So for the content of this class, I kind of want to talk a little bit more about the compilation process and what happened with like the linker object file and make file. All right. Should be relatively quick because at this like kind of like the second half of the class, I will then basically go over some more sample because we extend our linked list from Tuesday so that they can do more things like adding something in the middle, depending on where I want to add or delete some item if it match certain thing. All right. So now we know how C code get compiled to some extent, right? But internally, this is what happened. The first thing is you start to invoke what we call the C preprocessor. Preprocessor basically then process your C file, which is not just one single file. You have a combination of like 10 different .c files. The preprocessor would handle that well. Then it will compile your program. Then it will assemble your program into the .o file, which is something the computer can run. So the third step is when assembly comes in, and now the computer knows this assembly code, right? So it can then execute your program in the way you design it to. The fourth step is linking. It's link all your executable together, so the whole package comes into one single thing, right? So now let's go through the step one by one. The preprocessor basically this is essentially I go open your C code. Your C code is in what format? Text, right? It's a text file. Preprocessor read the text. I mean, if you think about it, your C file is just a bunch of string, right? Character, 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 character. If you write something like this, it's 3 character int, right? But what does it mean? It means that whatever is coming next will be tied with an integer, right? So now the preprocessor, one of the main tasks is it goes through your text. For example, when it goes to the word int, it now know, okay, I will look for the next thing that comes afterward. And I'll declare that thing is supposed to be a variable, maybe, depending on the condition, right? Maybe it's a variable, then I'll tie that to an integer. So it makes sure that it knows what the text means. Sometimes we call it tokenizing your file, which basically now break down your text into tokens. That means something. Variable, that's an integer. Variable, that's a character. Operator that adds A and B together. So that's what tokenizing means. This also process the header file. We do not see the header file yet, but in your assignment, you see some sample of that in one of the questions. These header file basically contain function definition, and most of the time it's actually pretty useful when you have to develop your code with your team. Let's say you have a project in a company that works with 5 people, right? One nice thing to do is to declare a header file with all the function that what it's supposed to do, with some comment that say, hey, this function takes this input, it do this. And you don't put in the function body, it just tell other people that if you call this function, this is what I expect as an input, and this is what you can expect as an output. So those will be in the header file. Then you have the define, whatever you define is done in the preprocessor. Again, when you do macro for the define, right? Let's say you build a macro for minimum A and B. The preprocessor will then process that and convert everything in C that match min parentheses to the actual minimum of A and B code. Anything that lives with the pound symbol also processed during this process, during the preprocessor. Then afterward, what it does is now it knows what the program is trying to do. It does start to tokenize your file into, like, for example, if I do A equal B plus C, right? These are the text that consists of A equal sign B plus C. C would then build it so that it has something, it would look something like this, right? B has an input, C has an input, produce the variable A. There's an operator, which is an add. you put in B and C, produce A as a result. So it will tokenize and make sure your program have actually like, if you will, right? It's not exactly this, but if you will, some kind of like mathematical meaning to what you're trying to do. All right. So what is pound defined? We talked about this already as a macro in your code, right? We already talked about the additional explanation. So I'll skip over this a little bit. Now the next step is compilation. All right. So now that you have a bunch of tokens, now the the program that you write is more meaningful to the computer. Becomes like operator. You have to perform this task. You can perform that task. The next thing is where a bunch of black magic happens. Here's what it does. The compiler, the reason why it's called a compiler is it takes out this token, it takes the definition of your hardware because the compiler is installed in your computer. So it knows, okay, you have the CPU from Intel that can run these commands, right? So it takes the token in, it generates, eventually generate assembly. The reason why I say eventually generate assembly is this compilation process also involves things like, I now know what the program is trying to do. Let me automatically optimize your program. And that's what the GCC compiler actually tries to do as well. For example, if I have a code that looks like this, int a equals 0, and then uses to printf hello world, and then that's it. That's your code, right? One thing you would realize is that you never use a, right? You declare that, you assign them to 0, and you never use it. If you compile this, it might actually even give you the warning that you declare that variable and you never use it. A smart compiler will actually get rid of that line. It will get rid of that line for you. It will do something, even something like this. Let's say you have int like I and j, right? And then some code here, and then you do I multiplied by j. It will even try to detect, hey, is there any possibility that I'm running this and j is 0? What does it mean if j is 0? The whole thing is 0. So it actually tries to do that analysis, change this whole thing to 0. So the compiler will do this all the time. There's also option you can feed in to optimize, like you can put optimization level on how aggressive this optimization can be. The flag is dash O with the number, like O3 will be, I will apply all the optimization known to GCC for this version on my program. In many cases, if you have a complex program, you might have realized it actually get a lot faster because it performs all this optimization for you. There's a lot of things, a lot of techniques that involve when you have to tokenize things. It's not easy from a text file, right, into something meaningful. So that process is like one semester worth of class already on how to tokenize a file, right? So that you can have language in Python, in Java, in C. What's the theory behind it? And then to optimize these things is like basically another semester worth of class on these are the tricks that the compiler can do to make sure eventually you get a faster code. But what happened is afterward you get the .s file, right? Basically, once you have this, the assembly step kicks in silently. The assembly step is, sorry. This is going to be, we'll do some of this in assignment for part B. But you convert assembly code, because now you have assembly code from the compiler. The assembler will generate the binary. Assembly code is like the human readable English-based language. The computer doesn't know what is like add A, B mean to them, right? The computer only understands binary. So this step basically convert from assembly instruction into the actual 1 and 0. the actual 1 and 0. This part is actually pretty simple, and it's basically read every single line here. There will be a huge manual by Intel and AMD to say, okay, for this instruction, it corresponds to this binary. And you just do that all the time. It's like a giant if else to make sure you generate the correct binary. Then, after you have this done, right, you have executable in binary format 1 and 0. The computer now know how to read it and how to execute everything here. The next thing is I have the object file. It means I can run my file, right? But in the big projects, right, you might not have just one C file, right? Because what I said so far is one C file. Sometimes you have 10 different files bundled together. That's main function in one of the file, and it calls all these functions, right? Now, that's where the linking process comes into play. Sometimes you compile multiple files, right? And then one main function in one of the file, and it knows, okay, run this first, and then it calls the other function. The object file that's generated will be then linked together, and you combine this into one executable, basically one file that contains everything that you can run. Now, let's say you have file 1 and file 2 and file 3 .c, right? You would then compile into file 1.0, file 2.0, and file 3.0. These are like different object files. Individually, these are what the computer knows how to run. These are ones and zeros, right? But let's say the main function is in file 2.0. What you have to do is now link them all together so the whole thing knows that, okay, run the main function here, then call this function. So on top of that, you have things like printf, right? The standard library you use in your program. It is not being compiled with your program. It's something you already know. It's something you can run and use, right? So those will be bundled together and linked together into a single executable, right? Then you can also have a dynamic library, which is not linked to your executable. It's not bundled together as a part of your executable, but it's actually called from your executable from somewhere when you run it. All right, when you run it. So let's talk a little bit more about that. Basically, library is like pre-implemented code that performs certain tasks. All right. This can be like standard io.h, standard library.h, and math.h. Okay. Static library, like what you seen earlier, was done when before you link. These are done at compile time. When you use the GCC command, it bundles the printf command, so you have executable. And let's say you port into another machine that has the same hardware but doesn't have printf library for some reason. That program will still run because it still knows how to run printf inside the executable itself. Right? So that's done in the compile time. When you combine the object file, right? These are executable. That's the static library. A dynamic library or anyone seen the .dll file in Windows? .dll. Those are dynamically linked library. Sometimes you run the games or something, for example, and it would crash and say the DLL is missing, right? Because it's not bundled to the executable. It's actually being called by executable with the assumption that when I run it, this thing will exist. Why are they useful? This can be library that the user install later. I install my game. I install, say, DirectX, right? And then my hope is that, look, if I install DirectX, this game can call this API because it knows how to do it. It will say, okay, let's say if I want to use dynamic library, right? At compile time, I don't care about whatever function of DirectX I'm installing right now. I can upgrade it later. Then my game can call the newer version of DirectX, which I just updated. So that's one of the purposes of having the dynamic library. You can kind of change the library before you run, after you compile. So this link operation happen right when the executable is run, not when it's compiled. You also in Unix, right? There's this thing called LD library path, which contain the path for your dynamic library. So when you use dynamic library, search that path and see where this API that I can run. If they exist, you run them. You also have the .so file, which is a shared library. It means the object file is shared among many programs. So each program can use it and it's shared at runtime. The sharing is done at runtime. There's also optimization flag. For example, you can optimize, well, you can disable all the optimization by doing -O0. But there are actually multiple level of optimization flag. So most of the time, O1, O2 are super safe. O3, most of the time they are safe as well, but there are some cases where your code can have random side effects, which we're not going to talk about it for the purpose of this class. If you do crazy thing to your code, O3 might not work. O3 is like, these are optimization that's super aggressive, but you need to guarantee, for example, your code has no side effects. It doesn't have weird things like go to instruction, things like that on your code, and it should work. For the most part, it will work. You can use -OG to also optimize your debugging experience. Basically, make sure when you do the -G, right? Now it can also run faster as well. One of the optimization that are super easy, right? It's called inlining. So one thing about function call in any program is when you call a function, it incurs additional overhead. You have to create the stack, you have to allocate the variable and things like that. And let's say your function is something super simple. I add A and B together. That's like my function call, right? You can use the keyword inline in front of the function definition. When you do that, the compiler would know that when you build the code, you don't actually call the function. You use the function inside the caller as if it's a part of the caller function. There's no additional function call happening. You replace the code inside the function on the main on the other functions, basically. There's no function call involved. You can turn the optimization flag that enable this small optimization, and you can see that the program also gets faster. All right, so that's it for the linker. Any question? All right. Quick pause. Can you wear your mask? Thank you. So the next thing I want to go over is makefile. This is super important because if you have to deal with C, C++, it's everywhere. It's everywhere. Think of it as an installer. Are you? Not sure. You might be too young. Have you been playing games that require an installer before the age of like you have Steam client to do everything for you, right? Think of it that way. Makefile is like an installer, right? So what is a makefile? It's a list of directions to build the program. So when you create a makefile, you just explain, these are the things that you want to do to compile and build your executable. The reason why it's useful is like for most team at all the companies, a lot of people will be updating the code, right? It's much easier to make sure I have one single makefile for these features that I can type make, and that's it. Everything is installed. All right. You can declare a requirement. This is called prerequisite. As the name suggests, prerequisite means that if this condition exists, we can make it. You can put in the set of commands each target. The target is the file that's going to be created. Basically, again, the purpose of the makefile is to generate the executable. Target is the possible file that is going to be created after you run the command. And the format is this. You start with the target name. It can be any name for your, like, it can be A, B, C, cat, dog, right? It can be the target name. Most of the time, use the same name as a .c file because it simplifies debugging. Then you have the prerequisite, for example, a dot like the file 1.c, file 2.c, file 3.c. It basically means that if I want to run this command, I will make sure that my directory before I build it has these files available. So let's say my prerequisite is like file a.c and file b.c. The make file will make sure that to compile this and run out the command, I'll check if file A exists, if file B exists. If it's not, it will complain that that file is missing. Fix it first. If both of them are available, then it run this command. It's as simple as that. Target, prerequisite, run the command. After you run the command, the target will be generated. So what goes into these commands? These are shell commands like rm, mkdir. You can basically generate a makefile that first create a directory and then run gcc, copy the executable to that directory, right? One of the common things to do is basically you would first generate a build directory. Why do we do that? It's actually simplify your whole infrastructure. You separate out the source code with the executable. So you have another directory called build. Everything that can be run goes in there, right? Then you combine. You do the linking, do whatever you want to generate executable, and then move executable to this build directory, right? But one more fancy things can be, if the file already exists, do this. If the file doesn't exist, do this first. For example, I can have a make file that cover program 1, program 2, and let's say both programs are used by program 3, right? My make file can first check if I have program 1 compile, if I have program 2 compile. If both of them are available, I don't compile program 1, program 2. I skip over compile program 3 right away. I can also, when I check it, if program is not being compiled, I only have program 2, and I only have the older version of program 3. In this case, I'll compile program 1. I'll bundle that with program 2 and then compile program 3 again. These are possible. So you can also, you can also assign variable to make files, work like shell. $sign come back to haunt you guys when you see make files. All right, it works the same way. This works the same way as shell. You can have phony target. For example, many make files will have the option to do clean. This option you can be invoked most of the time. You can run make clean. And it would, what it do is remove all the executable. So you have just the source file, right? But in this case, you're not generating any target. You're not generating any, there's no executable being generated. What I do is I just remove, right? So one thing I can do is I can have a phony target with the dot phony. So basically it's dot phony. And I put in some requirements that I want, right? And my command will be, for example, I do rm-rf build, right? This basically means that when I do make clean, right, I will remove the target. So in this case, if I do make clean, I just do phony clean. Then when I type in make clean, then I have a definition later that say, okay, if I do the command clean, I do rm-rf store.o, or in this case, rm-rf build, right, to go and clean up the executable, and I will just have the source file. We can also use wildcard. You can have the prerequisite be store.c. The make file apply the command on all the .c file in the folder. You can do make all. Usually there'll be this thing called all followed by multiple targets. When you type in make all in shell with inside the directory that has a make file, it will go to this all target. It means that I would do this followed by this followed by this. For example, this can be program 1, program 2, and program 3. If I want to build 3 programs at the same time, because the last program required program 1 and program 2, I can do this all, and then program 1, program 2, program 3. I can also specify the compiler. For example, I can set the compiler for C to be a specific version that I want. For example, I can do cc equal gcc. This means that every .c file will be compiled with the command gcc. I can do gcc-4.4. In this case, the .c file will be compiled with gcc 4.4. cxx is for the C++ compiler, but it works the same way. For example, on MacBook, you can do cxx equals clang. These are like the C compiler that are from a different framework called LLVM. Mac OS use this as the C++ compiler, so you can set the cxx flag to be clang. So you can also add the flag to the C compiler and C++ compiler by say C flag equals something something. It means that every time GCC is invoked, add this option. Add this option. The same thing for C++, which change from C flag to CXX flag. LD flag is in case you have to invoke any linker to link multiple object files together. You can also use conditional like if equal, if not equal. This is handy. For example, check the user ID of whoever is running the make file, so it can generate the directory according to the user ID and things like that. All right. I can also have a make file that call another make file. For example, if I download a bunch of programs and I have to make program 1 first, followed by program 2, I make sure I go into the program 1 directory, call make from there, go out, go into program 2, call make from there, go out, then make itself. I can do that. Basically, I can have a single make file that call another make file. Before I go through some more demo, I would first well, the demo will be on linked list, right? Insertion, deletion. So basically, we'll extend the linked list example, and then we'll follow up with your in-class exercise you have already from Tuesday. So please finish that so we can wrap up the first half of the semester, essentially. All right. So the lecture part, that's it for today. Make file linker. Any questions? Yes.
So for the optimization part, if we have like a header file, we don't use, so does it optimize and remove it as well?
That's a great question. Basically, for the header file, if we don't use it, the preprocessor will detect that already. So it basically preprocessor would know, okay, none of these functions is called. So we are not building that as part of your output. All right, so in that, yes, go ahead.
Can you show example of how it would look like when you do BIM editing of like a object file?
Like
So
if I have object file and I open it.
Yeah, like
Okay.
file.
Sure, let me do that quickly. So we go to lecture 8, which is the last lecture. We have a.out, which is conveniently been compiled binary. It's just 1 and 0. That's why I said the computer know how to run this. Basically, this is like a bunch of things. See how it includes the share library there, so somehow in the middle, right? So these are the .o file. Oops. All right, so again, as I said, we will extend this linked list example before we go there. Let me just take a quick break, like 10 minutes. We'll be back, continue that, and then continue the rest of our in-class exercise. I'll be here to answer any questions. Again, one more thing, tomorrow I will be here from 9 to 1 o'clock. The purpose of this is a long Q&A for both PCSA students and SYSkill students. This is like a makeup slot from one of the holiday we run into. PCSA student might come in and ask questions about their lab as well as their exam because they're having the exam like 48 hours exam that day. You guys can come in and ask any question about your assignment too, or any question about pointer and how you use things. I will be in 1402 from 9 to 11 and 1406 from 11 to 1 o'clock. If you want to do online, I'll be on Discord. Basically, you don't have to come physically. You can just join Discord. I'll be in one of the rooms, either SYSkill or PCSA. Just turn on the microphone and ask questions, share your screen, do whatever. All right? Yeah. Cool. Okay, so as I said, resume the demo. Now you want to delete. If I have this number everywhere on my list, I get rid of every occurrence of that number from the list. Okay. So I start from the front. I keep going until temp is null. What do I do inside? So to do, right, the first thing is check the value of our current node. Then to do.
How does this? So the type now basically means that if it goes beyond the linked list, it will become like a. How does it work? The type.
Oh, okay. So temp is a pointer to a node, right? And for each iteration, it will look at temp next because if right now, if let's say the node exists, it has two things, int, and then the pointer to another node. So I say every time I end my iteration, I will take the value of that pointer, which means essentially I go to the next node. But if that's the last node, temp next is gonna be null. So that means that at the end of my linked list, temp eventually will be null. Okay. All right. So now, so what we have to do is check the value, delete if the value match. Okay. There will be some issue that we are going to run into, but we go into some of these steps for now, right? So if temp value equals num, right? Delete. Otherwise, what? Do nothing. Keep going. Okay. So how do we delete it? If it match, it means that we are. Let's say the node is like this, right? A, B, and C, right? Let's say that's my linked list. A, then B, then C. Right now, we want to delete B, for example, right? How do we delete B? Yeah. Yes. Basically, A is next. Point to C, right? And then free B. I need to then free the node at the end to actually delete it. from existence, basically, right? What's the problem here? Yeah, we are at B. We have no access to A anymore because we already moved on from it. We can't just go, hey, B, go to the previous node. We don't have that. We can only go forward, right? So what do we do now? So let's say I have another temp, right? And at the end of each loop, temp2 equals temp. Will this fix my issue? Okay, that would be like in the beginning, I haven't assigned anything to temp2. That might get weird. So we go back to that. All right. Now, if I start to go into the loop, I start at front, right? Temp is not null. I check the value of temp. If it's the first node, we'll have to handle that differently. If it's not the first node, it guarantees that temp2 is going to point to what? So let's say we are at B right now, right? We go into the loop once. Temp was at A. Temp equals temp next. Make sure that temps now point to B. Temp2 equals temp means that temp2 points to A, right? So once you enter the loop once, temp2 will always point to the node before temp in this case. So in this case, points to A, right? So can we delete now? Because temp2 point to A, it means that the node A next should be what? Right? Because temp2 point to A, temp point to B. I want to make sure A point to C. So temp2 which point to A right now should point to temp which right now point to B. So B next is C, right? So I just need to do temp next. That will give me C. Okay. Then we free temp. Now, what's the problem? So quick thing, at the end of this loop, if I delete this, if I delete the node properly, temp is now free, right? At the end of the loop, I do temp equals temp next. At the end of that loop, I do temp equal temp next, right? But temp is free, so temp is like what now, right? It doesn't mean anything. It points to some. It's not now. It points to the old location, but your old location is not valid anymore because you free that. All right. So here's the first issue. We have to fix this part somehow, right? If we actually delete the node, where should temp be? Temp should now point to like listing of A, then point to B, then point to C, right? If we delete B, then temp should just point to C in the next iteration. But because we delete B, we can't point to C anymore because that connection is lost, right? So how do we fix this? What I would do, right, for example, is I can first of all get rid of this. I'll do this in my loop body somehow. If the number match, which means that I don't have temp next to work with, right? Once I do this, I free temp already, right? Temp2 next. Because temp2 is pointing to A, temp2 next should point to C by now. So I just can do this, right? Will that fix my issue if I match the number? It should, right? Now, the other thing is else, right? Temp equal temp next, right? So one more thing. All right, so we handle what happens to temp at the end of each iteration if I have to delete or if I don't have to delete, and now it should work, right? How about temp2? If I don't have to delete anything, I mean, temp2 should just basically follow temp, right? So it should be something like this. If I don't delete, I first make sure temp2 point to right the node right now, and then temp go next, okay? If I ended up having to delete, in this case, I delete B from the ABC link, right? Where should temp2 be? It should still at A. It should still be at A, right? So temp2 should point to the same node. Temp should point to C, right? So is this logic okay now? In the if clause, does temp2 move at the end at all? No, so it points to A. That's correct, right? How about temp? Temp is now pointing at C, also correct, right? Here, temp point to temp2 next. Temp2 next is A next, which is C, so it's also correct. If we don't have to delete anything, then temp move on, temp2 move on, also correct. Okay. Now, let me clean this up a little bit and ask you, will the loop be wrong?
The same point we first assign temp to,
Yes.
so it becomes A after deleting the value. Temp2 becomes C pointer.
Temp2, which one? Are we deleting or we not deleting at what is? Inside the loop, okay.
If we delete.
If you delete, okay, wait here.
So first we are starting
Uh-huh.
temp next to temp2 next here. Wait, could you explain that?
You mean this line, right?
The first line in the if.
So for the first line in the if, right, we want to delete B, for example, in this case, we want to delete B from it. Temp point to B, temp2 point to A. If I want to delete B, one thing I can do is to make sure first A doesn't point to B, A point directly to C. So temp2 point to A, so temp2 next should point to B next. All right, then I free B from it. Then I said temp is gonna equal to temp2 next because I freed the middle guy already. I now need to point to C, right? I cannot point to B anymore because B is gone. I now need to point to C, and that's the end of my loop iteration.
So it doesn't change the original value for temp2.
Right, temp2 stay the same. But if you are not deleting, right? Let's say temp is at B, temp2 is at A. At the end of the iteration, you're not deleting anything. So temp is pointing at C, temp2 points at B. All right. Now, when you're writing this, you need to think about the edge case, right? One of the edge case you mentioned already when you want to delete at the beginning, right? I want to delete A. What do we do? So here, before we go into this loop, maybe you want to handle if we want to delete the front node, right? Now, how do we do that? Now, in this case, we want to delete A, right, which is front. So the way we do this is actually pretty simple. We make sure, well, first of all, front point to B and free A, right? And we have to further, then what's next? If we delete A from it, right? It might be that the next thing we want to delete is also B. Like let's say your list is like 1, 1, 1, 1, 1, 1. And the number you want to delete is 1. So you should end up with just an empty list, right? So you delete the first one from your list, then you go to 1, 1, 1, 1, 1, which is still delete the first one again. Not recursion, just a loop is enough, actually, right? So one thing you can do is like while, right? Front, val. Well, obviously the first thing is if front equals now, like you have an empty list, return. Right? So this is one thing we can do. while front is not null, we definitely have to make sure that front is not the null value. If front is not null, it means that I can do front val, right? There's a quick thing in C, which is when do I evaluate these two statements? Because if you think about this, these are two things, right? Two operations. I check if this is null, then I check if value exists and it's equal to number or not, right? So that's the left side of the and the right side of the and. The way it works in C language is it goes from left to right. So in this case, it first check if front is null or not. Then it will check if value is matching or not. If we do the other way around, that's not safe because the first thing you do, I check the value. But if front is null, then everything will break down. All right. So this is what I can do. If I want to delete the front node, right? The first thing I do is say temp equal front, just to make sure I can actually like free them, right? And then front now move on to the next node. Like I have A, B, C. Front is at A, temp is at A. Now I do front equal front next, front equal temp next, the same thing because they are at the same node, right? Now front is at B, temp is still at A. Then I free temp. Now front move on, all right? Front move on. And I keep doing this until true condition. I keep doing this if I have front and the front number match things I want to delete. I will stop only when the front number doesn't match, which will allow me to go into the loop, the for loop, to get rid of the remaining number in my list. Or when I have an empty list, right? The other condition that I exit is front equals null. I delete everything from my list, right? So I can quickly move this here, right? Or I can even delete this, right? Because I said temp equal front. If front is null, I exit the for loop, I return. Same thing, it should work this way, right? Any question about delete? So let's try it. Now we have the print list and everything implemented, right? Let's make the array bigger, 10 entry. All right, let's do this for now. I count from 1 to 10, right? And I say delete node, right? Actually, what's the function name? I forgot. Delete with the number, right? So let's say I want to delete 6 and delete 4, right? Afterward, well, let's print 3 times actually. Before we delete, after we delete 6 from my list, after we delete 4 from my list, let's see how it would behave. All right, first, segfault. Something happened to my pointer. Why? Let's debug this, all right? Sorry, it stopped responding. So if I run, one thing that's kind of nice about segfault is you can run and let them segfault. If that happens, it will print the line the segfault happened on your face. Here, line 29, temp to next equal temp next, this segfault. When I see this line, one thing that pops up to me is temp to now is temp now. All right, because if temp2 is now, this will definitely segfault. If temp is now, this will also definitely segfault because both things doesn't exist. All right, so let's check that. Okay. So again, actually, one more thing that we can do. When you segfault, you can type the command backtrace. Backtrace will have the list of function calls that happen all the way from the main function. In this case, the main function called delete, then delete function segfault at line 29. It gives you a little bit more information about what happened. These are the series of function calls that we are deep inside here that cause the segfault. So let's go to line 29, right? And can someone think of the condition where temp2 is null? Or temp2 is some invalid location. Quick hint. If I haven't matched any number so far, right? Temp2 is going to take what temp is, right? So if I put in the value 6, for example, okay, so let's like the first call we try to do is delete 6, right? Delete 6. Definitely reach this line, and that causes segfault. Okay. Before this, temp val is not going to be equal. Something wrong here, first of all. Is that correct? Equal? Yeah. All right. But I don't think that's the issue, actually. Because if that's the issue, it means that something is wrong when I have to delete everything. Right? It means in this case, if I want to delete the first guy, it's wrong. Okay. Which that was actually my trap. So it should work now. Why does this work? So first of all, our logic, when we have to delete something in the middle, is correct over here. The reason why it is giving you the wrong answer is my equal sign is not correct, which means that when I go to line 29, right, in this line, it checks temp val, but instead of equal num, it assign num to temp val and return num, which is in the beginning return 1, right? In the beginning it returned 1. So it is become true. If true, so we try to delete the front guy. The issue is this is not supposed to happen, right? The while loop is supposed to trap that, because if I have to delete from the front of my list, right, it should be done here, not in here. Okay. So now let's change our list a little bit to test two things at once, right? I want to check if I can correctly delete the front part. I just do 6, 6, right? I want to check if I can delete two consecutive numbers. And I want to check if I can delete again, basically, right? So after I run this, it should just be 5, 8, 10. I delete all the 6, I delete all the 4. Okay. See? Now, as I said, if I need to delete at the front, it should be handled by the while loop. The bug is only that you have the equal sign that's wrong. It should be equal, not equal, because that's the bug where my condition that I'm checking is always going to be true, which means that I will always delete things, which happened in the first iteration, which we assume that we will go into the for loop knowing that the front is there and we don't have to delete the first number, because it should be handled by the while loop, which now is correct, now. All right, so that's delete node, right? How about insert at some position? Okay, so let's say I want to be able to insert number 10 into position 1, which is the second item, or position 0, which is the front item. So let's do that. All right. Before we do that, any question about demo?
Show the code again.
Huh?
Show the code.
Sure. Yeah, sure. Right. Let me move on a little bit and just use my hand here. Okay. Go from the online, I'm not here, but flow. What do I do here? Right. This will take care of the front part. This will take care of the rest of it. Basically, if I want that up at the front, this will take care of it. If I want to delete something from the front, it keeps on when I'm done with this. Just ensure that if I don't have it delete, if I have whatever is that now the front number is the number I don't want to delete. That's the first possibility. Second possibility, the front number doesn't exist anymore. I delete everything. I just go into this rule. If I delete everything, it exists right away. Sure. Right? So if I have to delete the rest of it, right? If the number, the front number is not the one you want to delete, but there's some more number here, you go into the loop. If it doesn't match, if it matches, because this guarantee that we have actually one number at the front, that's not the number we want to delete or import. It's one for sure. This guarantee that at least we get one point. So when you now find the first second, let's find the second gap. Always keep this pair on. If I have the earlier number now point. So we have two numbers here. One is this guy. This point here. This is on. The 10, which you would be pointing here now, point here. So one condition that you haven't really checked is like, what would happen if we delete from the end? Let's say we put number 4 here, right, at the end of my list. So instead of 10, it's 4. Should get rid of that as well. Will that break my code? Right, let's try that. And it's fine, right? Because we assume that if temp point to now at any point in time, it should stop. Okay? All right. So is it more clear now? All right. So let's do this. Void insert at in position. So one thing I want to be able to do, for example, is I want to insert, sorry. So I have a position and the input, right? I want to be able to, for example, insert at, I want to insert number 10 at position 0. So my list should be like 10 followed by something. Maybe number 123 at position 3 afterwards. And then number 5 at the position is way more than your linked list, like greater than the size of your linked list. Do that way. So I mean, I have an option. I can insert at the end, or I can just not insert. Right? Let's not insert. Okay. All right. How do we do this? So general logic, again, when you attack the problem, you have to think about, okay, if I'm human and have to go through my list, what do I do, right? First of all, I need to be able to point at the location I want to insert. If I'm inserting at 0, means that I should be able to point at the location 0, right? And I have to make sure that the node before me points to myself. So the temp2 and temp logic should still apply here. If I want to insert at position 1, for example, the first node need to be able to point to my new new data, and the new data should point to the old first node. All right. So let's say I want to insert x into a b, right? C, right? The list. You mean how do I know the list size?
So can we increase the list size without any issue or?
Yeah, because we always malloc, right? So there's no issue. So actually, that's the benefit of a list. You can keep adding things in without having to worry about the size. You want to make this into like A, X, B, C. Basically, put X at the first like the first location. Okay. What do we need? We need to make sure we stop at A, right? Because now A points to B. I know that this is the case, so I just make sure A point to X and X point to B. All right. So this is one of the key things I have to do. Stop right before we supposed to insert. Okay. Let's do again temp, right? Okay. Should be equal. All right. So basically this gives me the ability to go through my list, right? And I want to insert at a position. So it means I need to maintain some counter, right? I say counter equals 0. When do we stop? Should I stop when counter is less than num minus 1, num plus 1? Huh? Wait, what? Stop when what? Yeah. So let's say we stop at position. Okay. All right. Otherwise, we keep the counter up. We keep going until we are at the position we want to insert. Quick thing. If num is 1, for example, if num is 1, so counter initially is 0. Temp point to front. Temp point to front. Num is 1. I count up. Num becomes again. Position is 1. Counter is what? 1. So I stop. Where's temp? At 2. We stop one step too late, basically, right? So in this case, we want to make sure counter is equal to position minus 1. Okay. But we have to take care of what if we want to insert at the beginning, for sure, because counter start at 0. If I want to insert at position 0, this will not stop me. I'll go through the entire list and then I terminate. I return, basically, not terminate. I return, right? But if position is 1, for example, I stop where temp is at the first node, which is the right place. If position is 2, for example, if I want to put A, B, X, C, right? In this case, position is 2, A, B, then X, then C. Temp will stop right at B, because it start at A, go one step, B. Okay. So now, after I'm in this loop, I'm done. I know where I want to insert. Two things can happen. Position is longer than my list, right? This means what? What would cause my loop to finish? The null condition. So temp equals null. If temp equal null, return. I don't do anything to my list, right? Because my position way longer than my list. Else, now what do you do? Now I know where to insert. Yes. Yeah, basically go to like right now temp point to the previous node, right? So you just point to temp like new node. Basically, you want to insert, and a new node want to insert point to temp next. So basically, this is what we do. First, we make a space for the new guy, right? And then say the value equals num, because that's the number we want to insert. And then new node next should point to temp next, because temp next is the node before this. And it's pointing, like, let's say it's ABC and you want to do AXBC. Temp is at A, temp next is at B, so you want to make sure X point to B, so I can do this. All right, then temp next, instead of pointing at B, I want to point at X, right? So it's new node. And then that should take care of it. Now, the next question is, or what happened if front is empty? I mean, not front, if position is 0. Now, if position equals 0, else, right? If position is 0, it means that we want to insert at the front, right? So this is what we can do. It's actually pretty simple, right? New node equals malloc size of node. Same thing. We create a new node and say new node val equals num, right? Then what? Front point to I insert at the front of my list, right? So front should be new node. But before I do this, new node next should equal to front. Right now, let's say I want to do XABC, right? XABC, position is 0. Front point to A. When I insert the new item, X next should point to A. Front point to A right now. So I do X next, point to front. Then front, which point to A should point to X. New node point to X right now. So I do front equal new node. Then I return. And this is the condition that happened only. Huh? Oh, okay. So basically new node, let's just think of it this way, right? New node is X, the new guy you want to insert. I need to make sure this new node point to the old list, essentially. Okay. Because again, the old list is A, B, C. You want to do X, then A, then B, then C. So you need to make sure X point to A. What points to A right now is front, right? Before we insert, front points to A. So I do X next point to A. Then front, which is now at A, should be updated to make sure it now points to X, right? So I do front equals X right now is being pointed by the variable called new node, right? Which conveniently point to X right now. So in that case, new node has the position of X already. So front equals new node should work here. So basically, front, you know, right? So we add this guy and I just need to make sure new node X point to front point to new node. So afterwards, front should point here, this is front. This have the link already with new node next equal front
What happens if you switch?
If we switch the order, right? So if you switch the order here, you do front equal new node first. The issue is front point to the new guy, but the new guy hasn't pointed to the old list yet. So you basically lose where the old list is. Yes, floating in the memory is never being able to recover again. So let's try this. Oops, a bunch of errors. Line 29, something is wrong, syntax error. So let me go there. Oh, forgot the begin bracket. If you go to that line that says syntax error and everything looks okay, look before that line, it might mean something missing. And it thinks that that line is a part of the other thing that you have thoughts on. All right. See, so now you can insert 123, 10 at the beginning, say 10 position 0, right? So 10 appear first, then 123, then 10 again. So let me double check the code here. Wait. Yes, not correct actually. You insert 10, that's okay, right? Then I insert 123 at position 3, but somehow it's got insert at the front, right? So that's the first wrong one. Wait. So the list will be 10 followed by the old list. Afterwards, it will be 10 and then on at position 3, 123. And then number 5 should not appear because that's way over, right? Somehow 10 appears twice. 10 appears twice. 123 is at the wrong position. Likely something is wrong with.
We put one more case of the number being at the end.
Huh?
What happens if the number is at the end? If you put that as one of the.
Like if it's greater than position, you put it at the end.
No. Can you test like when could you scroll down once?
Yeah.
As one of the input tests, can you put one at the end as well? Just to see what would the result be.
Oh yeah, sure. I'll do that later because I kind of forgot the size of by now, right? Because we do a bunch of insert and delete. So inserting 10 at the front, that seems okay. If I do, let's just get rid of this, right? Because that already seems okay for us. I insert 10 at the front, that it seems to work. And then if we just insert 123 at position 3, it doesn't do that. It doesn't do that. And somehow we have this number 10 floating around, which is weird, right? So let's fix that. It's definitely something that has to do with the middle part of my insert at function. All right. So here, insert at. If position is not 0, right? Counter start from 0. When do I stop here? One thing I can do is basically test quickly, right? Counter equals %d and then new line, right? To make it super clear here. It doesn't even get print. Somehow we never go into this loop. So to double check, before we go into the loop, let's check counter and position, right? All right. See how that works. Okay, so for the first time counter is 0, position is 3, somehow looks okay, right? What's wrong?
the counter the name.
It actually has to do with counter equal equal. Does it ever become true? Zero and 3, are they equal? No. So it goes into that condition. It doesn't match. Exit the loop. Right? So when you exit the loop, temp is not now, so that's why always insert at position 1. Because it's going to loop exit right away. Okay. What we have to do to fix this is what? We keep looping until counter equal to position. We want to exit when counter equal to position, right? Is it position minus 1 or position? Huh? So let's say counter in the beginning, counter is 0, position is 1. We want to insert at position 1, right? We go into the loop once, which is too late. We want counter to be at 0 because we want to actually pointing at the front gap. So this should be position minus 1. Once counter equal to position, we want to stop, right? Once counter equal to position, let's say position is 1, it means that my temp should point to the first item in my linked list. If position is 2, I want temp to point to the first, not the first, the second item, right? Which means I go, if position is 2, I want to go to the loop once. If position is 3, I want to go through the loop twice. If position is 1, I want to just basically never go into the loop. All right. It means that I want to keep looping until counter equal position. And I want to stop when counter is equal to position minus 1. Right, so I can insert 123 as position 3 now, as you can see, right? That also tests by chance. We have linked list of size 3, position 3 is at 8, so we insert at the end. To test again, we can insert 10 in the beginning, insert 123 at the end. So the end should now, the linked list should be size 4 now, right? And then maybe test it one more time. Sorry. To put like random number in the middle of my list. Right. So 25 should be at position 2, and then number 10 should never exist. Okay. See. Number 25 is in the list, 10 is at the beginning, 123 is at the end of my list, and the last guy doesn't exist. Good. Just to make this a little bit more clear, right? Because I insert number 10 twice, I don't want to do that. Let's do insert 15. 15 should not be in my list, basically.
So this linked list, the number starts from 0 to the thing starts from 0. So like 1, 2, 3 starts from 0.
Yeah, position start from 0. Basically. All right, just clean it up so it doesn't print out a bunch of things. So you can, as you can see, like 15 doesn't exist. Okay. All right, so that's it for the demo today. Now let's transition to in-class exercise. For the in-class, right? You are basically for the lead code question, you are given two sorted lists. It can be something like this. I want to merge into one sorted list. So basically, after I run the code, it should happen. 1, point to 2, then point to 3, 3, then point to 4, 4, then point to 6, 6, point to 7. Basically, one single list. It involves a little bit more of the manipulation with the linked list. So it's a pretty good in-class exercise. Might take, if it's the first time you build a linked list, which in many cases for you guys, right? It might take some time. So feel free to like work with the TAs. Feel free to like work among your friends on like, hey, what's going on here? Why does it check false? Why does it not return anything? One more thing, lead code allow you to add your own test case, so that is going to be pretty useful here, because you might detect that, hey, you try to combine the list and some number is gone, or it's in a different order somehow, something like that, right? So if you build your own test case, it helps with the whatever condition you try to test easily. All right, so that's the end of my lecture today. Next week we'll resume with like data representation on how do we actually represent an integer, floating point, and all those things. Then that's it for the first half of the semester. Midterm will cover the material up until next Tuesday, all right? And then anything afterward will be the material for the final. All right, thanks a lot.